So we are going to study Maxwell equations and field theory. So this is my syllabus, laws and theorems, magnetic plane wave, boundary conditions, radiation, half-wave type, antenna arrays, communication antenna. So this is my syllabus, last one. We are starting our Maxwell equations and field theory. My syllabus is laws and theorems and electromagnetism, plane waves, boundary conditions, radiation, half-wave type, antenna arrays, communication antenna, performance characteristics. We keep it 8 3 dominate telecom external, not a deeper magnetic theory course. Maxwell equation, the big picture. Maxwell equation describes the relationship between electric fields and magnetic fields, which is represented by E and H. There are four fundamental equations. Gauss law for electric field. This symbol is del. Usually no delta symbol, triangular symbol, but suppose this symbol represents del, or we also say it nabla. Nabla dot d equals to this is dot product. D means electric flux density equals to rho means the volume charge density. Here this represents net electric flux equals to uh, net electric flux equals to electric fields. Okay, electric charges produce electric field. Net electric net electric flux entering or if a net electric flux is entering, then the charge is electric fields are outward. Sorry, what I'm talking. We will know it later. So Gauss law for magnetism. Net magnetic, there are no magnetic monopoles. So the net magnetic flux equals to zero. It is forms a closed loop. Magnetic field lines form closed loop. The electric fields are formed due to which electric charges. So Faraday's law. What is Faraday's law? This symbol represents curl. Del curl E equals to this symbol represents partial derivative. Okay, negative of partial derivative of V magnetic field. This represents magnetic field. Partial derivative of magnetic field. Changing magnetic field produces changing electric field. Sorry, changing magnetic produces electric field. That's the Faraday's law states. Here ampere Maxwell law. Here it is saying del curl H means magnetic field equals to J plus partial derivative of D means electric field. Change in electric field produces uh, J means here current. Change in electric field or currents produces magnetic field. That's the ampere Maxwell's law is stating. So, the last two are changing. The importance are changing electric field or produces magnetic field. Changing magnetic field produces electric field. So here you should know what is vector and scalar. Vector means magnitude. It only says the magnitude of what we are looking at, 350. This is magnitude. Scalar means it includes direction. Sorry, this is scalar. Scalar means only magnitude. It shows magnitude with the representative units. But vector means it represents also direction with magnitude. So 10 in x direction means a vector. For electric field, the four equations quantities we need to recognize. This is electric field represented by V by M. It tells us electric force direction and strength at a point. Tells us electric force direction and strength. The electric flux density. This is what we're looking at the Gauss law. Gauss, Gauss electric field. Gauss electric field. D del dot D equals to rho. And D is the electric flux density. The relationship with electric field in a simple material. D equals to permittivity, where E is the permittivity of material. So don't take D as the completely unrelated field. D equals to electric field, D is equal to electric field density. But D is not something unrelated. The electric field itself is D, but it is represented as D. Why it is represented, we look at later. Magnetic field intensity, H. represented by units are A by M, magnetic flux density B, units are Tesla, relationship B equals to mu H, where mu is permeability, B is magnetic flux density. So magnetic flux, field intensity, this is magnetic flux density. What is rho? The rho means volume charge density or charge density is the charge density. It tells us how electric charge exists for unit volume, unit cells C by M2. Another strange thing, okay, I explained all this. What is the partial derivative of this? Del is a gradient. It acts as a gradient. Divergence of gradient. What does curl mean? Curl means how much electrical change will circulate around or rotate around is the curl symbol. What it means. So what does this is partial derivative explain? What is okay? These are all expert. J means current density. You know everything here. Permeability. Uh, permittivity is used in electric fields or magnetic fields. We say permeability. This is spatial derivative operator. This is divergence. This is curl. So this is spatial derivative operator. With spatial derivative operator it down, we say called divergence. With this, both are called curl. Okay? Not axis curl, not dot. This is called divergence. This is called curl. This is partial derivative. Now your understanding is basically correct with one small correction. Okay. Here the net flux density leaving a tiny point volume is equal to the charge density present there. Here net flux means look at the imaginary box. It's an imaginary box, DRS of. There is a positive charge inside, electrical tends to spread out. So delta dot D is greater than 0 and therefore rho is greater than 0. If there were negative charges, the electric fields would point inward. Positive charges, that's why electric fields are outward. If the negative charges, then electric fields are inward. So the flux is entering rather than leaving, then it is less than 0. The important word is net. The what flux enters or net flux leaving the entering volume. More net deflux leaving means positive charge. More net deflux entering means negative charge. Equal entering and leaving is zero negative charge. Zero net charge density. Gauss law for magnetism. We say this is a closed loop. There are no magnetic monopoles for the closed loop. This is formed when we see a changing electric field produces magnetic field in a wire. So there forms a closed loop. So this is what divergence. Divergence of B equals to 0. There is no isolated magnetic field charge or magnetic pole elements. So there isn't a point where magnetic field lines taken over. Compared with electric fields can originate from positive charge and terminate on the negative charge. So electric fields will originate on a positive charge and terminate on a negative charge. So remember this line. Here there is no magnetic force. They form there is no ending, beginning or ending. So why does equation equals 0? Means the net magnetic force leaving any provided final volume is 0. Magnetic field enter one side of one volume. It eventually leave another side. The magnetic force entering equals magnetic force leaving. Therefore net magnetic force equals 0. Next, after this we see Faraday's law. This is curl of electric field equals to change in magnetic field. So, actually when I studied first Coulomb's law. Then I gone to Maxwell's gauss picture. That's what I studied. When I studied, started from F equals to K1 to the R square. From there onwards, I started uh, electric field and electrical starting the positive. So the positive charge produces an electric field pointing outward. The field is going outward in all directions. So if you put an imaginary closed circuit, Around the charge, this is the electric flux is passing outward through the surface, but your flux can enter and leave the surface. This is the important correction to simplify picture. Imagine several charges. Here, this is a charge. This is positive charge. This is negative charge. Uh, some field flux can enter imaginary surface, and some can leave it. What Gauss cares about is net flux. That means flux leaving minus flux entering. Flux leaving should be greater than flux entering. So net flux should be positive. So if for a charge, there are fluxes entering and leaving. Both are exist at the same time. But the flux leaving is the matters. That means when flux leaving minus flux leaving is greater than flux entering, then it is a positive charge. Flux. That means flux leaving minus flux entering is the value. For positive net flux, if more flux leaves, if leaving is greater than entering, then uh, charge density is greater than zero. There is net positive charge inside. Net flux, if more flux entering than leaving, then rho is less than zero. There is a negative charge density, charge inside. There is negative charge inside. Equal entering and leaving equals to energy entering equals to leaving, then net flux equals to zero, then therefore rho equals zero. There could still be electrical passing through the surface, they just have zero net flux. How this connects to what you already know, you can think of the progression like this. Coulomb's law of strongly two charges and as you electric field shades around it. Tesla electric flux density. So that's it. We understand what the picture now. Okay? What is net flux? What's next? I think we are saying something about lane waste. Ah, so plane electromagnetic waves. Exactly as listed in your. What is plane electromagnetic waves? The main idea is The main idea is actually very simple. A charging electric field creates a magnetic field, and a charging magnetic field creates an electric field. Together they can travel through the space of an electromagnetic wave. Think about a radio signal. This is a radio signal. Wave travels, electric field. So this is the H field is coming out from both electric field and direction. So the three directions are mutually perpendicular. Here electromagnetic field and magnetic field. The electric field and magnetic field are perpendicular to each other. The electric field is perpendicular to direction of propagation. The magnetic field is perpendicular to direction of propagation. So if the wave travels in z direction, uh, then E travels in y direction, electric field travels in the y direction, and H points in x direction. So we also look this in thumb rule, right? Right hand thumb rule in our physics class we get it. Why does it keep moving from a Maxwell's equations we just learned Faraday's law? Curl of electric field equals to yeah, partial derivative of magnetic field. Sorry, magnetic frequency. This also changing magnetic field creates electric field. Here answers for changing magnetic field creates changing electric field produces. This is changing magnetic field produces electric field. Sir. This is changing electric field produces magnetic field. Changing electric field or changing current produces magnetic field. Even though you know conducting current J equals to 0, it changing electric field can produce a magnetic field. So you get a cycle, you changes, it changes, it changes. And this distribution progress forward. That's an electromagnetic wave. So this is an electromagnetic wave. Plane electromagnetic waves, he said. Electromagnets itself are called plane electromagnetic waves. That's an automatic. Is it needed right? No. This is extremely important for communication. An electromagnetic wave can propagate to free space. That's how radio, television, satellite communication, radar, data, mobile communication can work without a physical link between transmitter and receiver. What does plane wave mean? Uh, don't imagine an actual flat object traveling through space. A plane wave means that at a given instant, the electric field has the same value across a plane perpendicular to the clockwise direction. For example, plane this is electric plane and propagation. These are electric field electromagnetic waves also. The plane wave means that at a given instant the electric field has the same value across a plane perpendicular to propagation. So this is plane. Like if you put a plane and see look at the propagation, the electric field waves are have same value. The wavelength is essentially plane. So remember these 4 points. So this is very important. Like don't I think confuse like electric field is perpendicular to propagation and these two are propagation, these two are not perpendicular. These two also are perpendicular. Like if you look into an accelerated axis like three-dimensional, so x-axis is perpendicular to z-axis, z-axis perpendicular to y-axis, y-axis perpendicular to z-axis. Like that H points in x direction. Okay, we'll study what next.